Well, thank you, Nino, for a very nice introduction. Also, thank Amrit for also inviting me today to discuss, something that we fell into not so long ago, where we discovered that actually NMR chemical shift was not only a nice number that allows us to basically, pinpoint and actually characterize molecule, but there actually is much more information hidden into it. And this story actually started as a dialogue between colleagues and friends, and I wanted just to share with you a bit of this story by discussing with people that we couldn't do with COVID for several times. But when you discuss with people, going to cafe, you can actually realize that there's many things that people do not understand. And there's a story between Richard Anderson, Oli Eisenstein, and Christophe Renaud, and Christopher Gordon. That's how we started, and many people joined this effort in trying to understand chemical shift. So how did it all started? So if you think about your undergraduate times, typically we take tables, okay, and we try to tabulate chemical shift. And typically, if you look at organic compounds, if I look at basically the carbon-13 NMR chemical shift, alkanes are typically around 0 ppm. We call that shielded value. And as you go to alkyne and alkenes, you get a bit more de-shielded, and you have the value, 80 ppm for alkyne and typically 130 ppm. For organic olefins, alkenes. Well, if you go from organic compounds to organometallic compounds, where you replace basically one of the pendant group by a metal, and I'm going to discuss today transition metals, the chemical shift window opens quite a bit. So you go from typically 0 to 150 ppm, which is classical, I would say, unless you discuss about ketones, to something which is much broader, which spans between minus 50 to easily 350 ppm. And it turned out that, again, you can see that you can distinguish metal carbon bound to sp3 carbon bound to a metal complex, or you can actually see in the green metal doubly bonded to carbon, and then you can actually see this metal carbon triple bond. And also what is actually interesting that we notice is that if I take at sp3 carbon, if the metal is positively charged, typically the chemical shift goes to higher and higher value, so more and more de-shielded. Similarly, if I look at metal carbon double bond, there is some kind of trend between 3D, 4D, and 5D metal. So for 5D metal, you typically have a very low value around, when I say low value, I mean around 100 ppm. And when you go to 3D metal, typically you have a very high value around 350, sometimes even 400 ppm. And I give you some example, below of classical organometallic compound. And what I will discuss today is organometallic compound, but what I'm going to say applies basically in a broader world of, any compound that you can characterize by NMR. In any case, so we started with that puzzle, and we were wondering, why this chemical shift window, why this trend, and that's how it all started. But before I go there, let's go back to basic, and let's go back to what I call, NMR, maybe not 101, but about 101, basically, okay? So typically, if I take the simplest possible compound with a double bond, because it will illustrate my discourse a bit better. So if I take ethylene, and you put ethylene in solution, typically you see a very nice narrow line around 120 ppm, 128 actually, exactly. While if you would actually take a solid state NMR spectrum of frozen ethylene, you have this typically solid state NMR spectra, very broad, with a very large breadth. And it turned out that it just tells you that chemical shift is depend on the orientation of your molecule with respect to the B0 field. Here you have a disordered solid, so you have basically a statistical distribution of all possible orientation of ethylene with respect to the B0 field. And in fact, as we say, chemical shift is a tensorial value, where you can actually divide that by what we call the three principal components of the chemical shift tensor, which can describe as the most de-shielded chemical shift, which is by nomenclature called delta 11. And in the case of ethylene, it corresponds of carbon NMR chemical shift when ethylene is oriented in that sort, which is basically where the pi frame is perpendicular to B0 field. While the most shielded position is when basically your molecule will be all aligned along basically where the pi system will be aligned with B0 field. And if you have ethylene, basically, which is actually positioned in such a way that you are, the CC bond is basically aligned with B0 field, you will have an intermediate, basically, chemical shift. And it turned out that obviously the isotropic chemical shift is what we measure in solution, is the average between these three values. And that's why basically in solution, because the molecule tumbles very fast, you get a single very narrow line, while in solid state, you get basically a very large pattern, which corresponds to all possible orientation of ethylene with respect to the B0 field. And delta 2,2, as you can see here, is a bit more intense, is because you have basically in that case an axis of symmetry, and you have many more possibilities to align that molecule with the B0 field. And this is what we typically do in solid state NMR. We spin the sample very fast around the magic angle, this famous angle which corresponds to 3 cosine squared theta minus 1 equals 0, so 54.7 degrees. And when you spin your sample fast enough, which means at a spinning rate which is larger than the anisotropy, you will basically get this isotropic chemical shift like in solution. But at any spinning rate intermediate between static and very fast spinning rate, you will get this spike. And the distance between these two peaks correspond to the spinning rate of your rotor. And you can see that as you go down in spinning rate, you start to reconstitute the shape of the so-called chemical shift tensor. Okay, and in fact, this shape is very much dependent on the hybridization of your carbon. So if you look at a tetra sp3 carbon like methane, which has a very isotropic electron distribution, you have a very, very narrow line. Well, as you go to sp2 and sp carbon, you see that your line gets broad in the case of the sp carbon because you have a C infinity axis. In the case of acetylene, you see that two of your components have the same value, and you have this very specific axial symmetric tensor. So you can, in a way, recognize a bit what you would see in EPR spectroscopy if you do a continuous wave spectrum. Okay, but obviously, as we spin the sample very fast, we typically don't see these values. Okay, and if I go one step further, typically we discuss chemical shift, but in fact, as you know very well, these chemical shifts are always referenced to a specific molecule. So in terms of carbon, typically you use a tetramethylsilane, but actually, if you calculate your chemical shift, you actually always calculate the so-called chemical shielding, which is an intrinsic value of your nuclei, which is referenced to compare to the bare nuclei. So in the case of carbon, it would be carbon 6+. Okay, so typically, in that talk, I will discuss invertedly either chemical shift or chemical shielding, and it's the same convention. Delta 1 is the most de-shielded component, the higher chemical shift value, and the most de-shielded component in chemical shielding is also sigma 1,1 and sigma 3,3. And delta 3,3 correspond to the most basically shielded component. So why do we have this very large anisotropy in the case of carbon, and while we never discuss that in the case of proton? Well, because in the case of proton, you have only s orbital, and actually what it turned out to be very important is this electron distribution around the nuclei. Okay, so typically, if you look at the Ramsey equation, you can actually divide the chemical shift into two parts. A so-called diametic part, which corresponds to basically an isotropic distribution of electrons around your nuclei, and this will be a shielding, okay? And this is mostly the core electrons as well as basically the deep valence electrons, while sigma para, which will give rise to this anisotropy in carbon-13 NMR and in any other nuclei, but at the exception of proton and spin orbit coupling, and here I will discuss mostly a parametric shift today. It is mostly due basically to this term, okay, which corresponds to the coupling of your field electron in basically occupied orbital with basically empty orbital of higher energy. And it turns out if you look at this equation, you can see that what is happening is that you're actually going to discuss this value is going to be large, especially if you have basically occupied orbital of the right symmetry that can actually interact with your vacant orbital via this magnetic moment operator. And this coupling will be particularly high if the difference of energy between the occupied and the vacant orbital of the right symmetry basically will be low in energy. So small number here mean big value here, okay? So as a chemist, if you think about it, and if you think about your organic chemistry lectures in your orbital theory lectures, you will basically immediately recognize that this is particularly high when the orbitals which are involved are what we call frontier molecular orbitals. So, and if I look at this magnetic moment operator, in contrast with a lot of operator in spectroscopy, but like what you would actually have in EPR spectroscopy or similar spectroscopy dealing with magnetism, the magnetic moment operator has the same symmetry as a rotational operator, which means that if I look in a pictorial way, when I basically have a magnetic field, it basically will induce a rotation of these electrons, basically, and it will correspond to basically the rotation of an orbital. Okay, so be careful, it's all pictorial. It has nothing to do with what I'm saying with quantum mechanics, because you cannot say that. In any case, if I look, for example, like if I come back to ethylene, if I look at my occupied high molecular, so occupied sigma orbital here, and I operate my magnetic moment operator around the x-axis, you will see that if I rotate my orbital, I will generate basically a pi star. And it tells you basically that basically in that equation, the sigma and the pi star have the right symmetry to interact via this magnetic moment operator. And because the energy of these two, the difference of energy between these two orbitals is small, then you will be much more de-shielded than, for instance, what you will have is a carbon in an alkane molecule. Okay? And basically, that's what this term is saying. That basically, if this term, if the symmetry of these two orbitals actually are compatible with the LX operator, basically, you will have an integral of 1. And if the difference of energy is small, you will have a large value. And this is actually what is happening in ethylene. Ethylene is de-shielded compared to a classical, basically, alkane, just because you have a small difference of energy between occupied and vacant orbital of the right symmetry. And in the case of p orbital, they have to be orthogonal to each other and orthogonal to the, basically, your operator. So what we're going to do now, we are going to measure chemical shift anisotropy, this chemical shift tensor. We are going to extract the principal component, okay? And what you can actually do by theory, you can actually calculate this principal component, and you can actually orient them with respect to a specific nuclei that you are measuring. And then what you can do is that we can do what we call a natural bond analysis, and you can do the same thing for chemical shift, and you can do what we call natural chemical shift analysis and actually understand which orbital contribute to the magnitude of this chemical shift. And in a way, you can actually show, you will see that you can actually extract from this paramagnetic shift how much is due to diamagnetic shift, which is basically often constant across a large range of molecule. And then you will have actually a part which will be basically modulated as a function of the molecule, which is this sigma para, and you can actually decompose this sigma para in which orbital actually contribute to this chemical shift. In a case of basically a double bond, what is very important is to have actually a small difference of energy between a metal sigma and your pi star, which should be empty. So let's come back to what I told you earlier, and let's look at again, can we try to understand a bit better the pattern that we see in this metal alkyl, metal alkylidine, and metal alkylidine? So a metal bound to single bond, double bond, and triple bond. So let's look at metal alkene versus an alkene. I remind you here the tensor of basically what you see for ethylene. And if you have a molybdenum or ruthenium bound with a double bond to a carbon atom, you can see that you see the same type of anisotropy, but you see that you have a much larger anisotropy. Your delta 1,1 is much more de-shielded than what you have basically for a classical carbon in the case of ethylene. And let's try to do the same analysis that what I've done for ethylene for this alkylidine molecule. And let's try to understand if we can see any trend that I told you earlier. So I will make a long story short. What we could actually do is we can actually measure, we can calculate, and we could show that the chemical shift tensor orientation and the sigma 1,1 is oriented perpendicular to the metal carbon pi system, similarly to what I discussed with ethylene. And the most shielded one is basically sigma 3,3 here, which is basically aligned with the pi frame of your double bond. Again, very similar to what you see in a olefin complex. And if you look at my several type of complex that I've shown here, whether I deal with molybdenum and ruthenium, you see that delta 1,1 is always oriented the same way. And if I look at all these numbers, the only one that actually changed a lot is this red value, this sigma 1,1. Actually, sigma 3,3 and sigma 2,2 are hardly affected by the type of metal I will be discussing today. It's not always true, but it is mostly true. And it turned out you can do this natural chemical shift analysis. And as I told you earlier, you will actually show that what drives the chemical shift is to have a high-lying filled metal carbon sigma bond close in energy to basically a pi star. Another contributor, which is of lower significance, is to have a high-lying field pi close in energy in a sigma star. You can actually expect the sigma star is very high in energy. That's why this contribution is much lower. And you can actually do the same analysis for sigma T2 and sigma T3, and you can actually see other type of orbital, and you understand very well why sigma 3,3 is actually not changing very much, because you are coupling basically a basically a sigma orbital with a basically high-lying sigma star. That's why very big difference of energy, low coupling for sigma 3,3, while for sigma 1,1, you couple basically a filled sigma with a low-lying pi star. That's why you have this very, very large difference of chemical shift for sigma 1,1. Okay? And based on that, as I told you, you can actually reconstitute your MO diagram. And this, in a way, it's, you have here the sigma, the pi star, and the sigma star. And what drives the chemical shift in this molecule is the energy difference between the sigma and the pi star. And now, without going too much into detail, now you can actually explain why you have this strand 3D, 4D, and 5D metal, because if you go back to basically your first lecture of condensation chemistry, you have all learned that basically if I go down the column from 3D to 4D to 5D, I increase the gap between my orbital. If I increase the gap between my orbital, the coupling becomes less efficient. And the reason why basically 5D metal are low chemical shift compared to 3D metal, like, so if I compare tungsten to chromium, chromium is a 3D metal, small difference of energy between the orbital, very large coupling, so you have very high chemical shift. So you explain why this metal carbon double bond resonate at 350 and 400 ppm for chromium, and why they resonate at 250 for basically tungsten, and why they are so shielded compared to ethylene. Well, if you think about an organic molecule, they are very, very covalent system, and the difference of energy between the two carbon is actually, the difference of electronegativity between the carbon is very low, but there is a very big difference between the filled and empty orbit and inoccupied orbital. While in the case of metal complexes, that's why they are reactive. The frontier molecular orbitals actually are very close in energy to the filled orbitals. So that's why you have this very big difference of chemical shift between transition metal complexes and across the transition metal complexes, 3D, 4D, and 5D metal. And I could actually spend my whole lecture discussing that and to explain many of the funny effects that are observed in this system. And I want today to show you a couple of examples that you actually see some differences between some systems. So now if I continue and I discuss olefin metathesis, because this metal carbon double bond are actually known to be very reactive for olefins and to basically exchange alkylidine. And the mechanism is very simple. You take this metal alkylidine, you connect an olefin, you make a so-called metacyclobutane, and if you continue the reaction and use the reverse way, you will basically exchange one olefin for another olefin. Okay. What is very important here is that actually we actually have found that this when you do this reaction, this 2 + 2 cycle addition, you make a metacyclobutane, and this metacyclobutane is directly on the reaction pathway for the reverse reaction, while this metacyclobutane can also isomerize to make a basically square pyramidal structure. And it turned out that this square pyramidal structure is involved in decomposition pathway. Okay, so why am I telling you that? Because it turned out that, again, if I look at these two type of metacyclobutane, there is some very funny trends in the literature. For instance, if I take a metal complex where metacyclobutane have been basically isolated, all the metacyclobutane which are in this green box are involved in metathesis, whether they are ruthenium, rhenium, titanium, or molybdenum, they are all involved in metathesis, and they are very funny chemical shift pattern. The alpha carbon is around 100 ppm, and the beta carbon is around 0 ppm. Okay. While all metacycles have been prepared in literature that do not participate in this reaction of metathesis have exactly the opposite pattern. The alpha carbon is around 40 ppm, and the beta carbon is actually slightly more shielded around 30 ppm, like you would actually expect in an alkane. So if you look at cyclobutane, you have something very similar, while here you have something that doesn't look like a typical organic molecule. Very, very big sort of chemical shift between the alpha and the beta carbon. Why is that so? So again, you can make this molecule, you can measure the chemical shift tensor, you can do the analysis, and I will show you it's actually a very, very funny pattern. In fact, it turned out that the chemical shift tensor of the metacyclobutane which is active in metathesis, is with this trigonal bipyramidal structure. So delta 1,1 component is perpendicular to the ring, similar to basically this delta 1,1 compared to the metal carbon, basically double bond. And it turned out when you do this natural chemical shift analysis, again, what is very important is to have a coupling between the sigma orbital and the low-lying pi star, okay? But what is actually funny here is that formally, here you have a sigma bond, but NMR tells you that this sigma bond has some kind of pi character. So there must be a low-lying pi star orbital, and this low-lying pi star orbital is possible because actually there is a d orbital which is pointing empty, which is pointing into the ring of that basically intermediate. And in fact, if you look at the frontier molecular orbital which are involved in driving the chemical shift of metacyclobutane, which are active in metathesis, they are the same molecular orbital which are involved in the metal carbon double bond, which tells you that basically this ring here should actually have some kind of double bond character. And in fact, interestingly enough, if I compare all the complexes which are known to participate in this reaction, where I take an olefin and a carbene to make a metacyclobutane, you can recognize that even though there are different metals, different electron configuration, D0 versus D4, there is always this empty orbital pointing into the ring. So the fact to have this low-lying empty orbital pointing into the ring drives the electronic structure of this molecule. That's why they have very similar chemical shift, and that's why this alpha carbon is deshielded. It is deshielded because there is a low-lying pi star, which obviously you don't see if you write the Lewis structure. But NMR tells you that Lewis structure is an easy approximation to help to draw molecule, but doesn't tell you anything about the reactivity of this molecule. And in fact, now, if I compare the metacyclobutane that do metathesis for the metacyclobutane that do not do metathesis, you can see that the one that do not do metathesis actually have either 2 electrons in that empty orbital. So sorry, it's not an empty orbital anymore, but there's 2 electrons in this d orbital, whether it is D0, D2, or D6. And in the case of the metacyclobutane, which has a puckered ring, the orbital is actually not in the plane of the ring. That's why the chemical shift goes from 100 to 40 ppm. And in fact, you can reclassify active versus inactive metacyclobutane just by locating where this empty d orbital is and whether it is empty or full, whether it is a D0 complex, D2, or if it is D0, D0, or D4, D6 complex. Okay, so here again, you can see very well this pattern across this system. And in fact, if you would plot the chemical shift tensor for the starting alkylidine, the metacyclobutane that participated in metathesis, and the one which does not participate in metathesis, you can immediately recognize just from the chemical shift tensor the electronic structure of the carbon. You can see that as soon as I isomerize my TBP into sp, I go from something that looks like a sp2 carbon to something which looks like sp3 carbon. So again, the chemical shift tensor is just giving you information about the electronic structure of this system. So let me now move to something maybe a more funny story, is that now if I go not to metal carbon double bond, but to metal carbon sigma bond, if I go and I compare alkanes to metal alkyl. Again, when I say metal, I mean transition metals. So if I go across that series, I have ethane, very small anisotropy because I have a sp3 carbon with a quite isotropic distribution of my electrons around my nuclei. Okay, but as I put a transition metal complex, I can see that I slowly increase my anisotropy. So if I go from this molecule to CP-tetraethyl trimethyl, this chemical shift tensor is a bit more anisotropic. When I remove one of the basically methyl group, when I go to CP2 titanium dimethyl, you can see that I have something a bit more anisotropic. And if I remove one more methyl group and I put a positively charge, I get a chemical shift tensor for sp3 carbon that looks like to me like an sp2 carbon. Okay, if I just look at this tensor, you agree with me that it will be very similar and very different from a carbon in a sp3 configuration. So NMR tells you already that just by looking at the chemical shift tensor, that drawing that molecule as a sigma bond is very likely incorrect. And in fact, you can do the same analysis And the reason why this molecule has such an isotropic chemical shift tensor is because there must be a high-lying sigma close to a low-lying pi star. And you may wonder, why do I have a pi star? Well, because here I have an empty orbital, which is basically in between these two cyclopentadienyl rings. And this empty orbital can actually interact with a p orbital, which is typically used to make basically my CH bond. Okay. And in fact, when I look at what NMR is telling me, I should actually write my CsP3 carbon with a very strong partial bond character and not as a sigma bond. And in fact, now you can actually see that when I discuss metal alkyl, I can imagine in terms of reactivity, it should be similar to an alkylidine. So I've just discussed with you olefin metathesis, where we have seen that a metal carbon double bond can react with an olefin to make a metacyclobutane, while formally, this bond should be able to react similarly to this olefin. Is that correct? Well, actually, if you go back to what we teach in organometallic chemistry, and if you discuss, the reaction mechanism, typically we always oppose two types of mechanism. We say that if you make a polymer from ethylene and a metal alkyl, you typically have a metal alkyl, you have an ethylene, you bind the system, and then when it is bound, then you can insert and you can make your polymer. And as you insert more and more, you make your polymer longer and longer. Okay, this mechanism is fully accepted, and that's what we teach in organometallic chemistry. However, if you look at in the 1970s, people say, well, maybe there's an alternative mechanism. Maybe the alternative mechanism is that actually this alkyl fragment, first, the H goes to the metal, you make a metal alkylidine hydride, then you bind an olefin, and then you do a 2+ factor addition, like in olefin metathesis, you make that intermediate, and then this hydrogen insert back, and you make a polymer. So, however, people have decided to discard that mechanism, because to do that mechanism, formally you go from a metal in an oxidation state to a metal in high oxidation state. And typically, the metal that do olefin polymerization are in D0 oxidation state. Therefore, this process is not possible. But what NMR is telling you is that actually the true story is it's neither Kersey-Harman nor Green-Rooney. It's in between. To insert an olefin to a metal carbon bond, you need to have this pi bond character. And this is only revealed by NMR spectroscopy, basically. So it's again an interesting, basically, thing that NMR can pinpoint a very important electronic structure which actually drives reactivity in basically catalysis. Let me go now to one of my last stories, where now we have seen metal carbon sigma bond, metal carbon double bond. Let's look at metal carbon triple bond. Okay, and here you have, like in the case of acetylene, if I look at the metal carbon triple bond, you have a very typical axially symmetric tensor where basically two of the principal components, the ones which are perpendicular to the metal carbon triple bond, are basically highly deshielded. But again, similarly to what I've shown you with metal alkylidine or with metal alkyl, the delta 1,1 is much more deshielded in the case of a metal carbon triple bond than in the case of a carbon-carbon triple bond. And again, if I look at the mechanism, it's very similar to what I've shown you with olefin metathesis. You start with an alkylidine, you bring an alkyne, you make a complex, you make a 2+2 cycle addition to make a metacyclobutadiene. Then in that case, you have one more step to isomerize this double bond to make another type of metacyclobutadiene. And then you make a new olefin and new alkyne by breaking this bond, okay? And in that case, this TVP structure can isomerize to make this kind of very funny square pyramidal structure that we actually call metallotetrahydrane as an equivalent to basically the organic molecule tetrahydrane. In any case, to make a long story short, what we actually found is actually the chemical shift of this carbon increases as you go from an alkoxide with more and more fluorine. So here there is no fluorine, 3 fluorine, 6 fluorine, 9 fluorine. And the chemical shift increases as you put more and more electron withdrawing alkoxide ligand. Okay. In parallel, you can see that actually the activity increases with the number of fluorine till it dies. And you may wonder, is there a parallel between carbon chemical shift and basically this reactivity? And in fact, there is a parallel. The only difference is that actually while in a case of electron withdrawing group, you can accelerate that reaction by having a more and more basically electron withdrawing ligand. When it is two electron withdrawing, you make a very stable metacyclobutadiene, basically, which does not basically participate in the reaction. Okay, so here again, we can see, we can actually understand the influence of the electronic structure of the starting material with the reactivity of the system. But the reason why I decided to discuss that story is that what I want to show you that this analysis that I've shown you with carbon NMR is not restricted to NMR, to carbon. You can actually go to other elements. And in fact, one of my very good friend at MPI has developed a whole series of metal alkylidine, especially has developed this new type of catalyst, and he started to measure molybdenum NMR. Okay, and he found some very funny trends. Okay, so here is a compound that he made. Okay, and you can see that if I look at my fluoroethyl alkoxide, the more deshielded my carbon chemical shift, the more deshielded my molybdenum NMR chemical shift. So you see there is some kind of relation between carbon NMR chemical shift of this carbon and molybdenum NMR chemical shift. However, for the compounds which are based on this siloxide, they do not correspond anymore. Okay? Funny enough, the best catalysts are all here. As I told you earlier, this is the bad catalyst because it actually makes very stable intermediate. And this one are very poor catalysts because somehow you need to have more electron withdrawing ligands. So why are these siloxide ligands occupying this position, and why the best catalysts have a molybdenum NMR chemical shift, which is around 450 ppm, while it's actually it varies very much for carbon-13 chemical shift? Why there is no total relation between molybdenum NMR chemical shift and carbon-13 chemical shift? So we embark in trying to study this relation. One caveat, obviously, is that carbon NMR is here. So it's actually quite receptive nuclei, and many of the probes that you have in your laboratory can do it. But there is like what I call a probe wall in NMR spectroscopy, which is around 915 NMR. And the reason for that is that actually, as you know, solid-state NMR has been developed heavily in the last 30 years, especially in the area of biomolecules. So if you look at chemical biology, you care about nitrogen 15, phosphorus NMR, carbon, proton, anything below you don't really care. And so most of the probe can do this part of the periodic table, but they cannot access this part of the periodic table. So we got interested, and even though some studies were done, obviously in the early 80s in this area. So we acquired a probe in that area, and we decided to actually study molybdenum NMR, which actually, if you look at molybdenum NMR, it is as good as carbon-13 in terms of receptivity. You just need a special probe. So either you make it yourself, or you need to basically talk to companies to help you to build a probe to access this type of nuclei. There is one more caveat in the case of molybdenum 95 NMR, is that molybdenum 95 is not a spin half, it's a spin 5 half. Okay, so there are several hurdles, because now not only you have the chemical shift tensor, but on top of it, you have basically the electric field gradient tensor. Okay, and it turned out that these two tensors do not have to be collinear. So these two tensors can also, so you have basically 8 parameters to be able to simulate your NMR spectrum. Okay. What you can do, however, is that you can actually help this by working at very high field, where basically as you increase the field, there is a direct relation between the field and your quadrupolar broadening. Okay, so as you go to very, very high field, and at ETH now we just have a 1.2 gigahertz spectrometer, and so we can actually have very, very narrow line. And the other trick you can actually do to have actually much narrower line is to use very high spinning rate. So again, as I've shown you with chemical shift anisotropy, the faster you spin, the less anisotropy. It's the same thing for the quadrupolar, basically coupling constant. I mean, not constant, but quadrupolar effect. So by spinning very fast and working at a very high spin, in principle, you can actually have very sharp line. Okay. Luckily, also in the case of molybdenum, often the quadrupolar coupling constant is not so large, so you don't have to spin that fast and to go to that such high field. In any case, we were able to measure this molybdenum NMR, and this is actually the molybdenum NMR at various spinning rate. You can calculate, you can simulate, and you can see that our calculation and simulation are not so bad. considering that the span, the difference of chemical shift between delta 11 and delta 33 is of the order roughly of 1000 ppm. So if I compare these two values, it's actually not so bad, okay? And in the case, as I told you, of this molybdenum NMR, you actually have a very low coupling constant, polypolar coupling constant of around 2 megahertz. Typically, you can actually easily go to 40 megahertz, and then it's nearly impossible to extract a very nice NMR spectrum. In any case, what we could actually show again is that we can actually show that the chemical shift tensor of molybdenum, again, is oriented very similarly to what you see for carbon, okay? But what is interesting is that delta 11 and delta 22 are basically perpendicular to the metal-carbon triple bond, okay? And it turned out that what drives the chemical shift is again delta 11 and delta 22, not so much delta 33. You have twice this component. And again, if I do the NCS analysis, we can again extract which orbital contribute to the chemical shift. And you can see here, what contributes the most to the paramagnetic shift is this orange label, basically orbital, which is a pi bond. So it seems that the pi bond is driving the chemical shift. And since you know the orientation of your chemical shift tensor, you can actually know with which orbital it is coupled. And it turned out this pi bond is coupled with a d orbital, which is interacting as a sigma orbital with this alkoxide ligand. Okay. So now if I compare my chemical shift tensor orientation for molybdenum and carbon, you can see this is the same orientation. Okay. And delta 11 is also oriented, and delta 2 are perpendicular basically to the metal triple bond, similarly to carbon. However, the orbitals which are involved in driving the chemical shift are different. In the case of molybdenum, it's a pi interacting with basically a d orbital which interact with the sigma frame of your alkoxide ligand, while in the case of carbon NMR, it is a sigma which is interacting with a low-lying pi star. Okay, so in fact now I can reconstitute my molecular orbital diagram of my molecule, and you can see that indeed my carbon chemical shift is driven by this sigma pi star interaction, while my chemical shift for molybdenum NMR is driven by a high-lying field pi with a low-lying sigma star, which is basically my LUMO. So interestingly enough, in the case of molybdenum NMR, we actually are probing the HOMO-LUMO gap, which if you think back to your organic chemistry, HOMO-LUMO gap tells you, oh, maybe and if you think about, all the Woodward-Hoffmann rule, maybe I'm actually driving reactivity. So molybdenum NMR is probing orbital, the HOMO-LUMO, which are directly involved in basically the 2+2 cycloaddition, okay? So in fact, if you calculate, and I will, the same thing for the phenol, the reactant and my complex, you can see that the metal complex, which are very reactive, have the HOMO and the LUMO, which is within the HOMO and the LUMO of my alkyne. This is true for all my complex with my silicon ligand, and it's actually not true in the case of the alkoxide. In the case of the alkoxide, either my LUMO is below the LUMO of my alkyne, but if you look at the HOMO of my molybdenum compound as a function of number of fluorine, you can see that it crosses the label. So there is basically, you are not anymore in the sweet spot for 2+2 cycloaddition. So NMR basically tells you that, if you want to be reactive, you need to have your HOMO-LUMO of your alkylidine, as shown by molybdenum NMR, right in between the HOMO-LUMO of your basically alkyne molecule. So let me give you one more story to illustrate that, again, it's not limited to carbon or organometallic compound. I will show you one more little story, this is my last story, on something that you have learned in organic chemistry in your childhood, in a way. Okay, so if I look at oxygen-17 NMR, it's also a nuclei which is a unfriendly spin because it's not a spin 1/2, but still, what is very interesting, if I look at this compound, these are peroxyl compound, you have two classes of peroxyl compound. You have H2O2, so-called TBHP, and these peroxyl compounds are known not to do epoxidation without a catalyst. And then you have this classical compound that you learn in organic chemistry, so-called MCPBA and DMDO, and these peroxide compounds are known to transfer the oxygen to olefin to make an epoxide. Interesting enough, these two compounds, which are two different classes, also have different cap of chemical shift in oxygen 17 NMR. This one are around 200 ppm, this one around 300 ppm, and the reason why this chemical shift is different is again because of delta 1,1. So delta 1,1 between this peroxide that do not do epoxidation and the peroxide that do epoxidation are actually very different in terms of chemical shift. And in fact, what you can actually show is that this chemical shift difference is only due to the presence of a different high-lying lone pair. Okay, and it turned out that the chemical shift difference is driven by the difference of energy between the high-lying field pi star of your peroxide unit with the low-lying sigma star. And now you understand what is the difference between MCPBA, DMDO, and H2O2 and TBHP. If you have this molecule, this is a cyclic molecule, and this one there is actually the H bond between oxygen and this oxygen and hydrogen. So you have a cyclic structure. If you have a cyclic structure, the two lone pair become coplanar. If the lone pair becomes coplanar, if the lone pair become coplanar, you raise the energy of this pi star. If you raise the energy of the field pi star, you decrease the gap between the pi star and the oxygen sigma star. And because you decrease the gap, you increase the chemical shift. In the case of H2O2 and TBBHP, you have a dihedral angle. Therefore, the pi star goes down in energy. If you go down in energy, you increase the energy gap between this pi star and the sigma star. Therefore, you go low in chemical shift. And now you can actually understand the reactivity difference, because again, what you can see is that the way you can describe epoxidation is a transfer of 2 electrons to the low-lying sigma star, but more importantly, the transfer back of 2 electrons from the high-lying pi star to basically your pi star orbital in the olefin. So again, I've shown you that again, with this very simple approach to NMR spectroscopy, you can extract electronic structure and relate a chemical shift to reactivity, and it actually makes NMR chemical shift a very powerful descriptor of reactivity. I will skip that. So now what my conclusion is as follows. I've shown you that basically chemical shift window, if I ignore proton NMR, is basically driven by this interaction with a high-lying field orbital with low-lying pi star of right symmetry. Okay, and this allows you basically to reconstitute the electronic structure of the molecular orbital diagram of your molecule and to understand the relation between the molecular orbital diagram and a chemical shift. And if you understand the molecular orbital diagram, you understand reactivity. Therefore, chemical shift becomes a very powerful tool to understand reactivity. We call that a descriptor of reactivity in our lab. And the reason for that is because NMR, similarly to EPR, this magnetic moment operator has the same symmetry as a rotation operator. And this is actually unique because if you look at any other spectroscopy, like IR or UV or X-ray absorption spectroscopy, these operators are actually typically translational operator, X, Y, Z translation. This one are rotational operator, and it allows you to connect sigma and pi symmetry orbital. And that's why basically NMR spectroscopy, and again, as EPR, is one of the best way to understand the electronic structure of molecule because they connect orbital of sigma and pi symmetry. And if you relate back to your undergraduate, basically childhood, you should immediately see that if you understand sigma and pi symmetry orbital, you understand reactivity. So again, my purpose today is to show this relation between sigma and pi star, pi and sigma star, and how you can actually understand electronic structure. With that, I remain to thank you very much for your attention. I'll be more than happy to answer your questions. Hopefully
thank you very much, Christophe. Now everyone has the chance to ask questions in the question and answer. I guess there's already one, and I will also have one, so we have some time to type your question. So there's one question by Joseph Zwanziger. It's my understanding that the paramagnetic and diamagnetic contributions are actually not gauge invariant. To what extent and how would this ambiguity affect your analysis?
That's a very good question. I'm trying to think how to answer that in a Bayesian way. It's a very good question. I have to think how to answer that. So far, we have not observed any bias. It is, so you have to be very careful in how you do your calculation, but we have no ambiguity, I mean, for me, between this system. So let me think about it. I'll probably send you back my answer in written because I have to think.
Okay. Okay. Then there's another question actually by Amrit, and he had to type it in the chat. But can you comment on the application of these methods to fully inorganic solids?
So we are working now on cadmium. So for example, if you look at quantum dot or basically zeolite, it's fully transferable. So I think to me, any analysis you do on one nuclei can be applied to another nuclei, and it is independent of the system that you are using. The limitation, which is due to calculation today, is that if you go to conductive material, where you have now band structure, there is no methodology that actually allow you to actually have this type of detailed analysis. But otherwise, anything including semiconductor, you can do the same analysis. What you have to be very careful about is that if you go to full inorganic material, especially if you have an element where you have a lot of spin-orbit coupling, then you have a new term, spin-orbit coupling, which typically go in the reverse direction of paramagnetic shift. And it becomes often very unnatural to understand chemical shift because while paramagnetic shift go in one direction, the spin-orbit coupling go into the other direction. And then it gets very difficult to actually, I mean, you can rationalize it, you can decompose it, but it's much more difficult to explain trends. So it's much more difficult. But otherwise, what I showed you today applies to any nuclei in any system. The caveat is when it goes to basically conductive material, where today there is no methodology to understand it, even though some people are working on it.
Okay, thanks. There's another anonymous question in the Q&A. Very interesting talk. I just wonder if there is a standard deviation in values calculated from the measurements, considering the solid spectra are normally quite noisy.
So what we have observed in terms of, so it's a spectra, as you know, some of them are not noisy. It also depends on the nuclei. Molybdenum is a case where I can tell you, you need very high field, you need a lot of work. And typically what we observe is that in the case of this very broad line, especially in the case of quadrinuclear spin, you need to work at several fields to make sure that your simulations are correct. You cannot actually base your simulation on a single field. Otherwise, you get very big mistake. But typically what we see is in terms of error is about, I would say, 20, 30 ppm for one specific principal component, okay? And for calculation, what we find is that there's always an error of roughly 10%, independent of the nuclei. So if you take carbon, 10% is roughly, 2 to 3 ppm. If you start to go to tanks and NMR, where we have chemical shift window of 10,000 ppm, then the chemical shift difference can be, 500 quite easily. And on top of it, if you start to have this heavy element, spin orbit coupling can become a major contribution. And then level of calculation you have to be very, very careful. So that's why what we do, and it maybe partially answer the first question, what we always do in our lab is that we do not trust isotropic chemical shift calculated. We always calculate the chemical shift tensor, and we compare to the measured chemical shift tensor across a series of molecules to benchmark our calculation, because you can very easily make big mistakes. For example, if you take double zeta basis set, often your isotropic chemical shift is good enough, but the principal components are wrong. So there is some compensation error, and you typically need to do triple zeta is minimum and quadruple zeta is better, and then you can actually even go to higher level of calculation. So this is what is very important, to be very careful when you do this calculation, especially with exotic nuclei. You definitely need to benchmark a little bit your principal component, otherwise you're going to get totally wrong. That's very important.
Okay. There's another question by Frédéric Blanc. Hi, Christophe, very exciting work. Can you also relate the reactivity to the principal components of the EFG tensors, oxygen, molybdenum, titanium?
So that's a very good question. So while I didn't discuss quadrupolar coupling constant today, because it's a bit more complicated in a sense that while chemical shift is driven basically by, I would say, electron distribution, quadrupolar constant is more about charge. So it's about the symmetry of charges. And so far, we have never found correlation between quadrupolar coupling constant and reactivity. But it doesn't mean it doesn't exist, but it has to be due with more of charge distribution in that case. So maybe if you go to more for reaction, which are pretty maybe more driven by ionic, principle, maybe that may work. But so far, we have not found any correlation. And we have not studied as much quadrupolar nuclei. And when we study quadrupolar nuclei, typically the CQ was not the dominating factor, even though it's not correct anymore because we have some new results. But that's, I'll tell you soon, Frederick, some funny story.
And there's another question by Eddie Dipp. Dear Professor Copéret, thanks for the great talk. May you comment on the AL location in non-equivalent crystallographic T sites in zeolites and its impact on zeolite reactivity? Does this location matter, or is it more an accessibility and diffusion issue?
So I think you have probably read our paper in JAX on these T sites. Right now, what we have found is that this quadrupolar coupling constant is very, very sensitive to the location. Okay. And maybe what you say is coming back to the question of Frederick. And I believe it's probably not untrue. I feel that when you have because a quadrupolar coupling constant is so sensitive to the position of basically the charge, my feeling, but we don't have enough data yet to really pinpoint that. That's why I didn't want to speak about it in details. I feel if you discuss about ionic reactivity like protonation, this may actually have an impact. So I think, yes, we see, for example, in T site of zeolite, we see difference of of quadrupolar coupling constant between 10 and 40 megahertz, which is not small, which means that this electron distribution is very different. I have a hard time to imagine it does not correlate with some kind of reactivity parameter. But I think this is all intuition now. We have no clear demonstration of that. But I think you are very likely correct. And in part, it answers the question of Frederick earlier, or question or comment of Frederick.
Okay, so just now one more just coming up by Fred Perras. A note on Fred Blanc's question: quadrupolar coupling is easy to rationalize in a particular case for oxygen, chlorine, etc. that have closed shell anionic structures. Their electric field gradients should be formally zero. You then have quadrupolar coupling being proportional to the covalency felt by the atom, particularly for terminal positions. Okay, I guess that's more a comment than a question. But maybe, do you want to say something, or do you just want to leave it like this?
It's a very good point.
Okay.
But I think it has to do with how your electron diffusion is rated. So covalence is important. But I really believe for certain reaction, it may correlate. This is part of what I told you about zeolite. But this is to be investigated. That's a very good point.
Okay. Then another one from an anonymous entity. Thank you for a didactic talk. I just wonder, would quadrupolar nuclei with very large CQ affect your calculations? Oh, so what we have found, I think it doesn't affect so much the calculation. The largest difficulty is the interpretation of your spectra, because if your CQ dominates the spectra, often your variation is in anisotropy for the chemical shift is so small compared to the CQ value that you cannot rationalize easily what you observe in terms of chemical shift. Because obviously, if you have a CQ of 40 megahertz and you have a change of chemical shift of 100 ppm, you have to trust. You are back to asking one of the questions earlier. How do you trust your principal component? So if you have no CQ value, I would say it's very solid. You can trust your principal component of the chemical shift tensor. When you have as we see for molybdenum, a quadrupolar coupling constant of 2 megahertz, still you can actually extract quite easily your principal component. If you have 40 megahertz,
your calculation would be fine, but you have no way you can benchmark them with any data, basically. That's one of the big problems. So I would say it's not a problem of calculation, it's really a problem of, can I trust my interpretation based on things that I cannot measure at all? Especially if this measurement, if you are looking at trends of, few hundred or thousand ppm and you compare to, megahertz spectra, that's where I see problems.
Okay, then one more question. So in an earlier response, you said that spin-orbit coupling needed to be considered, especially with exotic nuclei. In your experience, how large is the influence of spin-orbit coupling to the uncertainty deviations in your benchmarking?
Oh my gosh, this is a very good question. Again, most of the same we have studied so far, spin-orbit coupling was, few 5-10 ppm in carbon-13, not a big deal. When we did cadmium NMR for nanocrystal, this is the work we did with Kovalenko, then spin-orbit coupling is as large as CSA. So then, you can actually explain trends, but we never did any analysis of chemical shift tensor in that case, because, if my spin-orbit coupling is same magnitude as my isotropy, then I'm not sure I can really understand and actually develop a molecular picture, because now it's much more complicated to explain. So, but again, if you look at carbon-13 NMR, we never have found anything which is above 10, 20 ppm. Again, we didn't look into exotic cases. Like if I look at, for example, gold chemistry or like mercury chemistry with something bound to it, I would expect very large spin-orbit coupling. In that case, it's much more difficult to make interpretation. And the most difficult problem is to actually provide an intuitive, molecular picture I can actually teach in undergraduate, because then spin-orbit coupling is a bit more difficult to introduce.
Thanks. Then one more question by Daniel Klose. A very nice talk. By analogy to EPR, couldn't that also mean that one component of the G tensor along the MC metal carbon bond is most indicative of reactivity of a metal alkyl species?
I believe you are very nicely correct, Daniel. So I think, you can do the same analysis. So there actually, Martin Kaup has developed some program where you can do it, but often it's a bit more intuitive for metal complexes, because often the electron is localized in a very specific d orbital, and it's a bit more intuitive to know which one it is, while for NMR, it's less intuitive. But yes, what you say is actually correct. What I've shown today on NMR, you can do the same analysis with EPR, but I've never spent enough time, even though we discuss a lot, Daniel, together, I've never spent enough time to think about the EPR tensor in a similar way as, for example, to correlate, for example, the EPR tensor on titanium and try to be able to measure another nuclei and see how it correlates between the nuclei distance from this paramagnetic center. But good comment, Daniel.
I'll read also as a tough spectroscopic question. Can you also explain the activity trends in heterogeneous compounds where dynamics may partially average to carbon-13 CSA? Again, I think the problem here is measurement. So if you calculate, you are fine. Obviously, if you measure, it's a problem. Actually, all these actually studies that I discussed today derive actually from the PhD of Frédéric Blanc, when we were actually looking at the time of CSA, but we were mostly interested in dynamics. So we use CSA as a way to measure dynamics, and then it matured 10 years in my mind to actually look at CSA to understand electronic structure. So if you have dynamics, you average everything, and what you measure is not reality. Actually, recently with Alexander Yakimov, we look more specifically at aluminum NMR in zeolite, where here we were able to pinpoint a specific location of aluminum in position and structure. And here what we see that one of the big danger, and it's related to your question on dynamics, often people compare quadrupolar coupling constant measured at room temperature and calculated at 0 Kelvin. Okay, no surprise, it doesn't match. And this is true for solid. So if I take a zeolite, which people can believe to be solid, still the vibration is enough to go from 20 to 10 megahertz at room temperature. So big danger of dynamics. Always be careful what you measure. For most, I would say,
like spin half nuclei, you will have to have a ligand that moves some kind of, so that's less likely in heterogeneous catalysis unless you look at the ligand. If you look at metal NMR, where you could believe, because it's part of a structure, it's not dynamic, be very careful, because we got surprised by how much this dynamic can affect basically the quadrupolar coupling constant. Again, nothing surprising when you have seen it, but be aware that dynamic is part of the question. So very good comment, Amit.
So I think there's no more questions in the Q&A, but I have one more. So as a chemist, do you use these? Do you use the CSA also really as a design tool? I mean, now you rationalized all these findings, but do you also kind of go the other way, either in calculations or even measurements?
Yes. So, for example, we have a paper which we're about to resubmit with Zach Bergson, where we could correlate the reactivity to a specific structure. And so now what we can actually do is design. So I will not tell you the structure. Now we are designing material to actually adapt to try to generate that structure, because we found a correlation between a very specific structure motif and reactivity. Now we can actually do a reverse design. So we understand and then we can design. So one of the efforts we have in our group is to identify, among libraries of compound, basically descriptors, and then when we understand them, thanks to NMR, we can do a reverse design, actually know exactly what structure we want to make. So yes, this is the goal. It's not easy, but I think the more we understand electronic structures, the better off we are to predict where to go.
Of course.